Welcome! In this session, we'll explore LeetCode problem number 1014, best sightseeing pair. This problem challenges us to maximize a scoring formula based on array indices and values. It's a great exercise in optimization techniques, so let's dive in. The problem we're solving is called best sightseeing pair. You are given an array of integers called values, where each element represents the value of a sightseeing spot at a particular index. The goal is to find the maximum score for a pair of sightseeing spots. The score for any pair of spots, indexed as I and j, is calculated using the formula values I plus values j plus ij, where I must be less than j. This formula incorporates both the values of the spots and the distance between them, with the subtraction of j, I accounting for the distance penalty. For the input, you'll receive an array values with its length ranging from 1 to 50,000 in each element between 1 and 10,000. The output will be a single integer representing the maximum score achievable by choosing the best pair of sightseeing spots. Let's look at the first example where the input array is values equals 8, 1, 5, 2, 6. The output for this input is 11. This maximum score is achieved by selecting the pair I, j equals 0, 2. To calculate the score for this pair, we use the formula values 0 plus values 2 plus 0, 2. Which simplifies to 8 plus 5, 2 equals 11. If you try other pairs, none will yield a higher score. For instance, 1, 4, gives 1 plus 6 plus 1, 4 equals 4, which is much lower than 11. Now, consider the second example with the input values equals 1, 2. The output here is 2, and the only valid pair is 0, 1. Calculating the score for this pair gives values 0 plus values 1 plus 0 minus 1 is equal to 1 plus 2, 1 equals 2. Since there are only two elements in this array, this is the only possible pair. In the third example, the input array is values equals 10, 4, 3, 8, 1. The output is 17, achieved by choosing the pair I, j equals 0, 3. Let's break down the calculation for this pair, values 0 plus values 3 plus 0 minus 3 is equal to 10 plus 8, 3 equals 17. Testing other pairs, such as 1, 4, would give 4 plus 1, 4 equals 2, which is much lower than 17. Hence, 0, 3, is the optimal choice. This example highlights how the combination of high values and an acceptable distance contributes to the maximum score. By comparing all potential pairs, the formula ensures that both the values of the sightseeing spots and their positions are factored into the calculation. There are a few constraints and edge cases that need to be considered. First, for the smallest possible array size, when values contains just two elements, the output is simply values 0 plus values 1, 1, as there's only one possible pair. Next, the algorithm must handle large values since each element in values can go up to 10,000, meaning the sums can become quite large. Lastly, with the maximum array size of 50,000, an efficient solution is critical to avoid exceeding time limits. A brute force approach that checks all possible pairs would be too slow, so we need to consider an optimized approach that balances performance with correctness to handle these constraints effectively. To tackle the problem of finding the best sightseeing pair, we start by understanding the score formula values I plus values j plus ij. This combines the values at two indices, I and j, while also factoring in their distance. A straightforward approach is the brute force method, where we iterate through all possible pairs I, j, with I less than j and calculate their scores. The implementation involves two nested loops, where for each I, we check all subsequent j values, updating the maximum score as needed. However, the time complexity of this method is n superscript 2, making it impractical for large inputs, such as arrays with tens of thousands of elements. The space complexity is 1, which is efficient, but the quadratic time complexity is a significant limitation that makes this approach unsuitable for the problem's constraints. To overcome the inefficiencies of the brute force method, we turn to an optimized solution based on the sliding window technique. By rewriting the score formula as values I plus values j, we can break it into two distinct components, values I plus I, which depends only on the first index I, and values j, which depends on the second index j. This reformulation allows us to focus on maximizing values I plus I as we iterate through the array. Starting with the first element, we maintain the maximum value of values, I, plus I seen so far. For each subsequent j, the score is calculated using this maximum value and the current values, j. Afterward, we update the maximum value of values, I, plus I using the current index, ensuring it's ready for the next iteration. This approach eliminates the need for nested loops, reducing the time complexity to O(n), while maintaining O(1) space usage. The optimized sliding window approach has clear advantages. With a time complexity of O(n), it efficiently processes the array in a single pass, scaling well even for large inputs. Its space complexity of O(1) ensures minimal memory usage, as the solution relies only on a few variables. While alternatives like maintaining separate arrays for values, I, plus I and values, j were explored, these approaches require additional space, which adds unnecessary complexity. Ultimately, we chose the sliding window approach for its balance of simplicity and performance. It reduces the problem to a straightforward process of maximizing and updating values during a single traversal, making it both efficient and easy to implement. When comparing the two strategies, the brute force approach is simpler to understand but computationally expensive, making it unsuitable for large inputs. The sliding window method, on the other hand, leverages the insight that the score can be split into two independent terms, values, I, plus I and values, j. This realization, which is the key breakthrough, allows us to optimize the solution to O(n) time complexity. The trade-off is that it requires recognizing how to reformulate the problem, which may not be immediately intuitive. However, by adopting this approach, we achieve the best balance between simplicity and efficiency, solving the problem within the given constraints while handling large datasets with ease. The goal of this problem is to find the best sightseeing pair that maximizes the score given by the formula score equals values, I, plus values, j, plus ij, where I is less than j. This formula combines the values of two sightseeing spots with the distance between their indices factored in as a penalty. The challenge lies in solving this efficiently, as the constraints require us to go beyond a straightforward brute force approach. By breaking down the formula and understanding its components, we can identify ways to optimize the solution. Let's explore the steps to achieve this. One way to solve this problem is by using a brute force approach. The intuition here is to calculate the score for all possible pairs, I, j, where I is less than j, and then track the maximum score encountered. To achieve this, we initialize a variable max_score to a very small value, then use nested loops to iterate through all pairs of indices. For each pair, we compute the score as values, I, plus values, j, plus ij and update max_score if the current score is higher than the previous maximum. Finally, we return max_score. However, this approach has a time complexity of O(n) squared due to the nested loops, making it inefficient for large input sizes. To address this, we need to look for ways to optimize the computation. A key insight is that the formula can be rewritten to separate the terms into values, I, plus I and values, j, which opens up opportunities for optimization. The optimized approach takes advantage of the rewritten formula, score equals values, I, plus values, j. Here, values, I, plus I depends only on I and can be pre-computed as we iterate through the array. This eliminates the need for nested loops. We start by initializing two variables, max_score, which will store the maximum score encountered, and max_I, which keeps track of the maximum value of values, I, plus I seen so far. Then, we loop through the array starting from index 1. For each index j, we calculate the score using the current max_I and values, j. If the score is greater than max_score, we update it. After calculating the score, we update max_I by comparing its current value with values, j plus j. This ensures max_I always reflects the best sightseeing start point up to the current index. By the end of the loop, we return max_score as the result. The key to the optimization is how we update max_I. After computing the score for a given j, we update max_I to include the current index. This ensures that it always represents the best values, I, plus I for all indices less than j. The time complexity of this approach is O(n), since we traverse the array only once, and the space complexity is O(1), because we use only a few variables without relying on additional data structures. This makes the algorithm both time and space efficient. By leveraging these insights, we achieve a significant improvement over the brute force solution while maintaining simplicity in implementation. The algorithm uses no extra data structures, relying only on variables to track max_I and max_score, which keeps the space complexity minimal. Breaking down the formula into independent components is a key insight that simplifies the problem. By separating values I plus I and values j, we can dynamically update max_I as we iterate through the array, ensuring it always reflects the best possible value up to the current index. This allows us to calculate the score for each j in constant time while maintaining the optimal solution. The single-pass approach ensures efficiency with O(n) time complexity. Additionally, this method handles edge cases such as small arrays, arrays with negative values, and arrays where all elements are the same. For example, in the case of small arrays, we compute the score directly without iteration. If the array contains negative numbers, the formula still works as intended, and for arrays with equal elements, the algorithm correctly identifies the pair with the largest index difference. Let's walk through an example with values equals 8, 1, 5, 2, 6 to see the algorithm in action. We initialize max_I to values 0 plus 0, which is 8, and max_score to a very small value. Starting from j equals 1, we calculate the score as max_I plus values 1, 1, which equals 8. We update max_score to 8. Next, for j equals 2, the score is 11, so we update max_score to 11. For j equals 3, the score is 7, which doesn't change max_score. Finally, for j equals 4, the score is 14, so we update max_score to 14. Throughout this process, max_I is updated dynamically to reflect the best values, I plus I seen so far, ensuring the algorithm remains efficient. At the end of the iteration, the maximum score is 14, which is the result. This implementation solves LeetCode problem number 1014, best sightseeing pair, using an efficient greedy approach. The goal is to maximize the score for a pair of sightseeing spots, I, j, where I less than j and the score is defined as values, I plus values, j plus I j. The key observation is that the score can be rewritten as values, I plus values, j. This allows us to decouple the problem into two parts, maintaining the maximum value of values, I plus I as we iterate through the list, denoted as max_I, and calculating the score for each new j as max_I plus values, j. ## line-by-line explanation. 1. Initialization. We start by initializing max_score to 0, to store the best score found so far, and max_I to values, 0, the best value of values, I plus I at the beginning. 2. Iterate through the list. We loop through the array starting from index 1, since j greater than I must hold. 3. Calculate current score. For each j, we calculate the score using the formula max_I plus values, j. If this score is higher than the current max_score, we update max_score. For update max_I, we update max_I to ensure it always contains the maximum value of values, I plus I up to the current index. This ensures we have the best possible I for any future j. 5. Return the maximum score. After iterating through the array, we return max_score as the result. ## complexity analysis. Time complexity. The algorithm runs in O(n), where n is the length of the values array, as we iterate through the list just once. Space complexity. The solution uses O(1) extra space, as no additional data structures are used. This greedy approach is optimal and handles all edge cases, including small arrays and arrays with negative values. This is the Java implementation for LeetCode problem number 1014, best sightseeing pair. The logic mirrors the Python solution, where we iterate through the array to calculate the maximum score for sightseeing pairs. Key differences include the use of Java's math.max for comparisons and type declarations for variables. The solution maintains a running maximum for values, I plus I, and evaluates potential scores efficiently in a single pass, ensuring O(n) time complexity. To solve this problem, we start with the input array values equals 8, 1, 5, 2, 6. First, we initialize two variables. The max underscore score is set to 0, which will keep track of the maximum score we find. The max underscore I is initialized to the first value in the array, 8, because at the start, the best value for values, I, plus I is simply the first element itself. In the first iteration, where j is 1, we calculate the score for the pair, I, j, using max underscore I. The formula is max underscore score equals max, previous max underscore score, max underscore I plus values, j, j. Substituting the values, this becomes max, 0, 8 plus 1 to 1, resulting in a max underscore score of 8. Next, we update max underscore I to reflect the best value for values, I, plus I so far. It becomes max of the previous max underscore I, which is 8, and the current values, j, plus j, which is 1 plus 1. The result is that max underscore I remains 8. Now moving to the second iteration, where j equals 2, we again calculate the score for the pair. This gives max underscore score equals max, 8, 8 plus 5 to 2, which evaluates to 11. The max underscore I remains unchanged because max, 8, 5 plus 2, is still 8. In the third iteration, where j equals 3, we calculate the score for the pair, I, j. Using the formula, the score becomes max underscore score equals max, 11, 8 plus 2 to 3, which evaluates to 11. At this point, max underscore score does not change because the new score is not greater than the current max underscore score. Then, we update max underscore I. It becomes max, 8, 2 plus 3, which is still 8. In the fourth and final iteration, where j equals 4, we compute the score as max underscore score equals max, 11, 8 plus 6 to 4, which again evaluates to 11. Here, max underscore score remains unchanged as no higher value is found. Finally, we update max underscore I to max, 8, 6 plus 4, which results in a new max underscore I value of 10. At the conclusion of these iterations, the maximum score we found is 11. In this second example, we are working with the input values equals 1, 2, 3, 4, 5. Again, we initialize max underscore score to 0 and max underscore I to the first value, which is 1. For the first iteration, where j equals 1, we calculate the score for the pair, I, j. Using the formula, we get max underscore score equals max, 0, 1 plus 2 to 1, which evaluates to 2. We then update max underscore I to max, 1, 2 plus 1, resulting in a new max underscore I value of 3. Next, in the second iteration, where j equals 2, we compute the score as max underscore score equals max, 2, 3 plus 3 to 2, which evaluates to 4. Afterward, we update max underscore I to max, 3, 3 plus 2, resulting in a new max underscore I value of 5. In the third iteration, where j equals 3, we compute the score for the pair, I, j. The formula gives max underscore score equals max, 4, 5 plus 4 to 3, which evaluates to 6. At this point, max underscore score is updated to 6. We then calculate max underscore I as max, 5, 4 plus 3, resulting in a new max underscore I value of 7. Now in the fourth and final iteration, where j equals 4, we calculate the score as max underscore score equals max, 6, 7 plus 5 to 4, which evaluates to 8. This updates max underscore score to 8, which becomes the final maximum score. Finally, we update max underscore I to max, 7, 5 plus 4, resulting in a new max underscore I value of 9. Thus, for this example, the maximum score is determined to be 8. In this third example, the input values are 9, 8, 1, 2, 3. As always, we start by initializing max underscore score to 0 and max underscore I to the first value in the array, which is 9. For the first iteration, where j equals 1, we calculate the score for the pair, I, j. Using the formula, max underscore score equals max, 0, 9 plus 8 to 1, which evaluates to 16. This updates max underscore score to 16. Next, we update max underscore I to max, 9, 8 plus 1, which results in max underscore I remaining 9. In the second iteration, where j equals 2, we compute the score as max underscore score equals max, 16, 9 plus 1 to 2, which evaluates to 16. As the new score doesn't exceed the current max underscore score remains unchanged. We then update max underscore I to max, 9, 1 plus 2, which still results in max underscore I being 9. For the third iteration, where j equals 3, we calculate the score using the formula max_score equals max, 16, 9 plus 2 to 3, which evaluates to 16. Again, max_score remains the same since no higher value is found. We update max_I to max, 9, 2 plus 3, which results in max_I staying at 9. In the fourth and final iteration, where j equals 4, we compute the score as max_score equals max, 16, 9 plus 3 to 4, which also evaluates to 16. As such, max_score remains 16. Finally, we update max_I to max, 9, 3 plus 4, which keeps max_I at 9. At the end of this example, the maximum score we achieve is 16. To analyze the time complexity of our solution, we can break it down step by step. First, we initialize two variables, max_score and max_I. Since this operation does not depend on the size of the input array, it is constant time, or O1. Next, we iterate through the array using a for loop that runs from index j equals 1 to len, values, 1. This means the loop executes n 1 times, where n is the length of the array. Within each iteration, we perform a few arithmetic and comparison operations to update max_score and max_I. These include addition, subtraction, and a maximum comparison, all of which are O1 operations. Since the body of the loop executes in constant time for each iteration, the overall time complexity of the loop is O(n), as it scales linearly with the size of the input array. By summing up the contributions, we can conclude that the total time complexity of the solution is O(n). Now, let's evaluate the space complexity. The algorithm is designed to operate in constant space, or O1. First, the input array values is provided as an argument, so it does not require additional memory allocation. Second, we use only two scalar variables, max_score and max_I, to store intermediate results. These variables require a fixed amount of memory, regardless of the size of the input. Furthermore, the solution does not utilize any additional data structures, such as arrays, stacks, or hash maps, to store information. As a result, the memory usage remains constant. This in-place processing ensures that the algorithm is space efficient and does not grow with the size of the input array. To better understand the efficiency of the optimized approach, let's compare it with a brute force solution. In the naive approach, we would evaluate every possible pair, I, j, or I less than j, and compute their corresponding score. This requires two nested loops. The outer loop iterates over all indices I from 0 to n1, while the inner loop iterates over all possible j values from I plus 1 to n. The total number of iterations is the sum of the series n1 plus n2 plus 1, which simplifies to n*n1/2. This results in a quadratic time complexity of O(n squared), as the number of operations grows exponentially with the size of the input. In contrast, the optimized solution eliminates the need for nested loops by maintaining a running maximum value, max_I, and calculating the score for each index in constant time. This drastically reduces the time complexity to O(n), making it far more efficient for large inputs. The optimized solution achieves its efficiency by leveraging the pre-computed value of max_I, which tracks the maximum value of values, I, plus I encountered so far. For each index j, the pair score is calculated using this pre-computed value in O(1) time. This avoids redundant computations and ensures a single linear pass through the array. When analyzing different scenarios, we find that the algorithm consistently achieves O(n) time complexity. In the best case, even if the array is sorted or the maximum scores appear early, the entire array is still processed. On average, the algorithm iterates through the input once, maintaining its linear complexity. In the worst case, with no discernible pattern in the array, the algorithm still performs a single pass, adhering to O(n) time. The reasoning behind this is straightforward: each element is processed exactly once, and no additional data structures are used. With its O(n) time and O(1) space complexity, this solution is both time efficient and memory efficient for any input size. When solving this problem, there are several common pitfalls to watch out for. First, many beginners overlook the importance of the I-j penalty term in the formula. They focus solely on maximizing values, I, plus values, j, without factoring in the distance penalty, which can drastically reduce the score, especially when j is far from I. Another frequent mistake is resorting to a brute force approach. While iterating over all pairs, I, j, might seem intuitive, this naive O, n superscript 2 solution becomes impractical for large arrays, such as when n exceeds 10,000. To solve this problem efficiently, you need to optimize beyond brute force. Additionally, the optimal approach hinges on maintaining the best values, I encountered so far as you traverse the array. Forgetting this critical step can lead to redundant calculations or suboptimal results. Lastly, it's easy to make indexing errors, especially since j must always be greater than I. Be careful to avoid computing scores for invalid pairs where j is less than or equal to I, as these off-by-one errors are common but preventable with attention to detail. Now, it's also important to avoid overcomplicating your solution. Some candidates unnecessarily introduce advanced data structures like heaps or segment trees. While these can work, they add complexity without improving the performance over the simpler linear O(n) approach. Instead, focus on breaking the formula into two key parts, values, I, plus I, and values, j. This decomposition is the core insight that allows for efficient traversal and real-time updates. In interviews, your ability to explain this optimization clearly is often more important than just arriving at the solution. Be sure to highlight why brute force is inefficient and how your approach avoids redundant computations. Additionally, be prepared to address edge cases, such as arrays with only two elements, the smallest valid input, or arrays where all values are identical. Finally, interviewers might ask follow-up questions, such as finding the top k pairs instead of just the best single pair or imposing additional constraints like limiting the maximum distance between indices. Understanding how to adapt your solution to these variations demonstrates a strong grasp of the problem. This problem also connects to several related problems, which can help you identify patterns and refine your approach. For example, LeetCode 122, Best Time to Buy and Sell Stock 2, shares a similar concept of maximizing profit through forward traversal. Another related problem is LeetCode 53, Maximum Subarray, which involves maintaining a running maximum to optimize the solution. Similarly, LeetCode 918, Maximum Sum Circular Subarray, introduces the idea of maximizing sums under circular constraints, which can expand your thinking about edge cases. Finally, LeetCode 42, Trapping Rainwater, emphasizes the importance of pre-computing values to achieve an efficient solution. Exploring these problems can deepen your understanding of optimization techniques and help you tackle variations more confidently. There are several approaches you can consider for solving this problem, each with its own trade-offs. The brute force method, which involves iterating over all pairs, I, j, and computing the score for each, is the most straightforward to implement. However, it's highly inefficient for large inputs due to its O(n) superscript 2 time complexity, making it impractical for arrays with thousands of elements. A more efficient approach is optimized traversal, which leverages the decomposition of the formula into values, I, plus I, and values, j. By maintaining a running maximum of values, I, plus I as you traverse, you can compute the score in a single O(n) pass. This method is both scalable and highly efficient, though it requires careful implementation to avoid logical errors. Finally, there's the divide and conquer approach, which involves splitting the array into two halves, solving each half independently, and merging the results. While this can be a good exercise for practice, it's more complex than necessary and not recommended for interviews. For real-world scenarios and time-constrained settings, stick with the optimized traversal method. Great job following along. To wrap up, we applied an efficient approach to solve the best sightseeing pair problem, achieving optimal time and space complexity. Remember to practice breaking down complex problems and keep exploring other optimization techniques. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!